Alrighty, welcome to the fourth part of the second stage of deep learning in NLP. So far, you know exactly what attention is, you know exactly what self-attention is, and you know exactly what a self-attention sublayer is. And as you have seen, the entire sequence can be processed at once when you pass in the Q, K, and V matrices and get the output, get the Z's at once, corresponding to the input sequence. This is all done via matrix multiplications and matrix operations. Now, let us talk about the idea of attention heads. Okay, so far, you know that your deep learning parameters are randomly initialized, right? So you randomly initialize your, weight matrices, Q, K, and V, and many other parameters in your network. And you go through some optimization and will output some optimal set of parameters that easily get you to the result, or more accurately produce the intended result. But what if we had a different initialization? What if our a W, Q, K, or V were initialized differently? Would we at the end of the day have a superior model? Would we faster converge, or would it affect the network more negatively than positively? These are all possible scenarios if you use one set of initializations as opposed to the other. That's why in training we may try various random initializations, because you may end up at a regime of parameters that's advantageous to your training paradigm. In a multi-headed attention paradigm, you try all of them at once. You try various initializations. You try various set of parameters in parallel, and you call each one an attention head. So you can have H attention heads in your self-attention layer. Here you can see two attention heads, each one starting from a different set of initial values, a different regime of values, and you run them at the same time, and then you somehow combine them into final Z value. This has been shown experimentally to improve the performance of your network. That's the mathematical explanation. But conceptually, it's as if you look at the same sequence from different perspectives, and in a lot of sequential processing, including language, you can have you can emphasize different parts of a message and interpret it differently, although it's the same sequence. So a same sequence can emphasize various messages, various types of information to be conveyed. And conceptually, you can think of it that way. You can think of it as starting with a different mindset, different context, for example, different perspective from the sequence. So formally, you concatenate the output of each attention head, and then you multiply that by the matrix WO to get your multi-head attention representation, right? To get your multi-headed attention representation, and each head, would just operate as normally, as we talked about earlier, on the Q and W matrices to create the attention representation Z's, as was mentioned earlier. So this part you know very well. So the only new part is that now you have multiple attention heads, so you concatenate them, and then you multiply them by a matrix to combine them. Linearly. And well, you concatenate them, and then you multiply them by this matrix to linearly combine them and get your multi-headed representation, and to also bring them to the size that's desirable, which would be Z. Here you can see this visually, so you concatenate all these, representation of these two item, sequence of a sentence, right? You have, your representations, concatenate them. You multiply them by WO, and then you get your Z final multi-headed self-attention representation Z. Okay, then let's everything together now. Basically, you had some Z of dimensionality of your model and embedding, right? So you had your embeddings as an input, 512, size 512. Then you created your KV and Q matrices, right? Over there, the dimensionality of K, V, and Q vectors were reduced to 64, right? Then this is because your WQ, WV, and WK weight matrices are of size RD by D sub K, which outputs vectors of size, and DK, which is 64. Now, if you remember, these encoder cells, these encoder layers, need to be to have the same input and output, and self-attention layers need to have the same size of the same values, but the same size of input and outputs, because they can be repeated, right? And to do that, you need this WO to bring them, to bring all these vectors from size 64 to 512. So your WO is RHD, RHDV, which is 64 by D of model 512, bringing all the vectors back to 512, to size 512. So the resulting matrix, the output matrix of Z vectors, will be the number of items in the sequence by 512, which is your dimensionality of the model, or embedding Z dimensionality, which are 512. All right. As mentioned earlier, the output of the self-attention layer, multi-headed self-attention layer, the outputs will go towards the next sublayer, which is a feed-forward neural network. Each Z position has its own feed-forward neural network with a dimensionality of 2048. Both input and output vectors are 512, as shown earlier. These feed-forward networks within the layer are identical. They use the same weights within the layer. But if you go to the next layer, it would be a different set of parameters. So within the layer, they're identical. Across layers, they're different. Formally, what happens is your input goes through two series of linear transformation with a nonlinearity in between. Your input gets multiplied by a W1 with additional bias term, then goes through the ReLU nonlinearity, for values smaller than 0 and 0, output 0. For any greater value, it will be the same value. And after the ReLU nonlinearity, it will go through the second linear transformation, which is just a W2 weight matrix multiplication and the additional bias term. All right, beautiful. So far, we successfully parallelized our attentional, recurrent network. Now we have a parallel transformer architecture that has linear transformations, has nonlinearities, and is fully parallelizable on a GPU. That's amazing. We have lost, however, one piece of information, and that's the sequence. So nowhere in our network we indicate, no representation actually knows so far knows, where the words are, which word comes after me, which words come before me if I'm a word, because all it is a vector multiplication and an attended over one. Nowhere, no representation actually so far includes any positional information. That's why we need positional encoding. Simply put, positional encoding is a series of sinusoidal waves. These waves come in varying frequencies over the components of a vector. So basically, your positional encoding is a vector of varying frequencies across components and gets added to the input of your encoder or decoder. So they get added directly to the input of your encoder, which is just the original embeddings, and decoder that you'll see in the future what is. But they're added at the initial step of your encoder and decoder to give an idea of, so that each word actually has an idea, exact idea actually, of its position relative to every other word around it. In the equations, sine and cosine equations, I is the component of the positional encoding vector, and POS, position, is the position of the word. So for example, ja over here can have position 0, and sui can have position 1, so on and so forth. This will result in wavelengths stretching from 2 pi's to 1,000 times 2 pi's. So this is what happens. You have your input, you get your embeddings, from your embedding dictionary, and then you add your positional encodings. That is different and unique per word in the sequence. All right, that brings this video to an end. I'll see you in the next video.